Hello, in the last chapter we learned how to graph linear equations, and we saw how it's easy to visualize the slope and what the slope stands for, and we can kind of get a picture of what the equation looks like. In this chapter we're going to be solving systems of linear equations, and I'm going to show you how we can do that visually by using a graph. So we're going to start with this problem here. Scientists studied the weights of two alligators over a period of 12 months. One alligator had an initial weight of 4 pounds and grew at a rate of 1.5 pounds per month. The other had an initial weight of 6 pounds and grew at a rate of 1 pound per month. After how many months did the alligators weigh the same amount? Well, what we can do is for each alligator we can make up an equation that shows the growth rate. So if we say this first alligator here had an initial weight of 4 pounds and grew at a rate of 1.5 pounds per month. So if we say m equals number of months, and we could say w equals the weight of the alligator, then the first alligator would have a weight of 4 pounds plus an extra 1.5 times the amount of months. All right, so at time 0, meaning at the beginning of the experiment, the alligator weighed 4 pounds. So if you plug in 0 here, 1.5 times 0, you get 0 plus 4 is 4 pounds. Now after 1 month, we plug in a 1 here. 1.5 times 1 equals 1.5, and then add the 4, it's now 5.5 pounds. So here is an equation for its weight after a certain amount of months. Now for the second alligator, it's going to weigh 6 pounds at the beginning, and then it's going to grow at a rate of 1 pound per month. I don't really need that 1 there. I could just say m, but just to show that 1 there. So 1 pound per month, 6 pounds. Now if I want to graph these, I can use months on the bottom here or on the side, but I'm going to use usually the independent variable will be graphed on the x-axis, so we're going to do that. And let's say we'll go each line will equal, let's make it worth 1 month each line. Alright, so this will be 2, and 3, and so on. And then the weight, let's see, how much are we going to get up to here? I'm not quite sure. If we go up to 10 months, the weight could be, I don't know, up to 20 pounds. So let's say let's say each line is worth 2 in this case. So this will be the pounds. So this is pounds, and this is months down here. Alright. And so we're going to go 2, 4, 6, 8, and so on. So if I want to graph these two equations, I'll probably start by putting them in slope-intercept form. So we have 1.5 m plus 4. That gives us an intercept of 4. So we're going to start there. And when we use our slope here, which is, I was going to write m equals, but that makes it a little complicated being that m is our variable in this case. So I'll just say the slope equals 3 over 2 in this case. Now when we're using slope, we have to keep in mind what our scale is. So we have a rise of 3, so we're going to go up 3 grid lines here. But a run of 2 means to the right 2 grid lines, but technically these grid lines aren't correct, right? I'm using 2 spaces to indicate 1 unit. So instead of going over 2, I'm going to have to just go over 2 units on the month. So up 3, 1, 2, 3 units, and then over 1, 2 units, right? I need to be at the 2. And we can do that again. 1, 2, 3 over 1, 2. We should get a straight line here. 1, 2, 3 over 1, 2. And I can make a straight line, so let's do that. And let's make it red. Okay, So it's essentially going like this. All right, now let's graph the blue one. Put that in slope-intercept form. So it's 1m plus 6. I'm just going to write m plus 6. So 6 is our intercept, and our slope is 1, or 1 over 1. Okay, so up 1 over 1 unit. So remember, it's 1 unit. So up 1 over 1, up 1 over 1, and up 1 over 1. Okay, up 1 over 1, up 1 over 1, something like that. So let's make that blue, starting here and going like this. Okay, so now we have two graphs on one, or two lines graphed on one coordinate grid, and they each represent the growth rate of two different alligators. So what does that tell us? Well, what we have here is a point of intersection. So it looks like here the weight is the height of the graph. So at the beginning, the blue alligator weighs more, and the red alligator weighs less. And then as time goes on, the red alligator is growing faster. And so at this point here that I circled, which is at 4 months and 10 pounds, so 4, 10, the alligators weigh the same amount. And then after that, the red alligator continues to outpace the blue alligator in growth. And so what you can see real easily is a visual interpretation of the answer, after how many months did the alligators weigh the same amount, is right at the intersection of these two graphs. So let's try a new example. Here I have two equations and a graph, so I'm going to graph these on this coordinate grid here. So y equals x plus 2 would start with a intercept at 2, and it has a slope of 1 over 1, so something like this. And then I'll graph that. Alright. And now it extends in both directions, so make sure you show that. And then let's graph the blue one here. So it starts at -2 for the intercept, and it has a slope of 3 over 1. So 1, 2, 3 over 1, 1, 2, 3 over 1, 1, 2, 3 over 1, and we can make our straight line in blue, starting down here and going up through there. Don't forget to extend it out in both directions and have an arrow on it. There we go. So we can see here that these two equations are intersecting at this point right here, which is 2, 4. And if we were to plug in 2 and 4 for each equation, we would get 2 plus 2 equals 4. And for this equation, 2 times 3, 6, minus 2 equals 4. So notice, any point of intersection on the graph will also be solutions to both equations. If you pick any other ordered pair on this whole coordinate grid, it will not work for both of these equations. Okay, it might work for one of them, but it won't work for both. This is the only point on the grid that works for both equations, and therefore we call that a solution to this system of equations. Okay, let's try another example. So I have two more equations here. Let me grab a graph. Okay, and this first one's not in slope-intercept form, so I could put it in slope-intercept form if I wanted, but what I'm going to do is just use an XY chart. So if it might be easier to choose for y in this case, so I'm going to say if y is 1, 2 minus 0 would be 2, and in fact if y was 2, then 4 minus 2 would be 2, and then if y is 3, then x would have to be 4. So let's graph these. So we have 0, 1, and then we have 2, 2, and we have 4, 3, 4, 3, something like that. And we can make our line now, something like that. And don't forget to extend it out in both directions. We don't know where it's going to intersect, so we want to have everything covered here. Alright, now let's go to the blue equation. This is in slope-intercept form, so that'll be easier. It's like 1, and then slope is up 1 over 2. Slope is up 1 over 2. Oh, interesting. So as you can see, these lines are overlapping exactly. So there's going to be an infinite amount of solutions. So the reason that happens is because these actually are the same equation. They look different because they're in different forms, and that's actually why I didn't put the top one in slope-intercept form, because then you would see that it is exactly the same as the blue one. I'll show you now. So if I solve for y here, I'm going to get 2y equals x plus 2. If I divide by 2, I get y equals 1/2 x plus 1. Okay, so there are times when you'll get two equations that look different because they're in different forms, but they actually are the same equation. And we say that those equations coincide and that there's an infinite amount of solutions. Okay, let's try another example. If we have y equals 2x plus 2, and if we have y equals 2x minus 1, these are both in slope-intercept form, so it should be pretty easy to graph. Oops, it didn't work. Let's try that again. There we go. Okay, so we'll start with the black one, and we have 2x plus 2, so 2, and then a slope of 2 over 1, so up 2 over 1, up 2 over 1, up 2 over 1. Now we can make our line. Okay. Something like that. Don't forget to extend it in both directions. Alright, and now we can do the blue one. So it starts at -1 and has a slope of 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and we can make our line. Something like this. And we'll extend it out in both directions. And you can see, oops, that these are parallel. And so there is no solution because there's no intersection. There is no xy coordinate that would be true for both of these equations or both of these lines. And so we would consider this no solution. Okay, so the three things that can happen are a solution, and we get the coordinates. We could have infinite amount of solutions, right? And that happens when the equation is the same or they coincide. And then we can also have no solution, and that happens when the lines are parallel. And that's it. Thanks for watching.